Howdy and welcome back. So, depending on how this lesson's broken up for the current semester, we're at probably 30 minutes right now. I'd recommend going ahead, taking a break and then coming back, and then you can continue on through this, but we do need to get through this material. So here we go. Conceptual inheritance walkthrough. So we're setting up, and this is going to use some just kind of abstract types in a sense. We're going to, and I don't mean that in the C++ way, I mean it in the way that they're kind of insensible. So we'll have some class parent, which we're just going to use to illustrate an inheritance scheme and some of the implications of how objects are going to be constructed, copy assignment, destruction, etc. So one important thing to note is that if you do not provide a default constructor, then the compiler will create one for you. As we will note here in a minute, if you do not specify otherwise in the derived class, the default constructor of the base class will be called implicitly. So where am I going with all this? What we're going to see here is that if we were to create a fire truck, depending on how we've defined default construction for fire truck, and let's say we haven't, both the default constructor for the base type, in this case truck, would be invoked, as well as the default constructor for the derived portion of this of FT, which would be fire truck. And what we can think about is we've kind of got going on in memory a truck portion as well as a fire truck portion of the object. And the base class is going to be responsible for setting up the base portion of that object. And the derived class is going to be responsible for setting up the derived portion. And that is why what we see here is default behavior would be that in the derived class, if we're creating an object of the derived type, the default constructor of the base class will be called implicitly to go ahead and respect and set up the base portion so that any sort of invariants that we have defined on that component are maintained. Okay, so a couple things here. If you do not provide a default constructor for this child class that we're setting up here, just child, it's inheriting public from parents. So a child is a parent, which is, I don't know, kind of weird, but just bear with me. So if we do not provide a default constructor for child, then the compiler is going to create one for us. And it's nonsensical. It's not doing anything fancy. But anywho, one's defined. So as we note in a moment, if we do not specify otherwise in the derived class, the default constructor of the base is going to be called implicitly. And this is how we define the base class's constructor. Whoops, there's a destructor there too. Let's just focus on the default constructor. This doesn't do anything interesting except print out the address of the object that's being created and communicate that, hey, we're in the base class default constructor. So if we go ahead and just create child P, notice here that the parent constructor was automatically called. And we'll get into this in a bit more, but also notice that the parent's destructor was implicitly called as well. So again, there's, and notice that we haven't even defined a default constructor for our child class. So just, understand if we haven't defined this, the base classes, if we haven't specified otherwise, the base class's default constructor would be called implicitly. As is here, the derived class's constructor is also called implicitly. So we have two constructors firing off implicitly for the to create our child object P. Now let's go ahead and define and declare and define our own default constructor for the child class. It's doing pretty much exactly the same as the base. It's printing out the address of the object and then specifying that, hey, we're in the child's constructor. So if we go ahead and look here, and we're doing the same for the destructor as well. If we go ahead and create that child object P, so just child P, here's what's observed. We see that the parent class or parent class's default constructor is called implicitly. Notice here, I never explicitly invoked it. It's called implicitly forced. The default constructor of the base class is called implicitly. Notice that after the base class portion was set up, so for our child P, we set up the base portion first. Let me just call it parent. And then after the base class portion is set up on top of that, we build up the child portion. And that's what's shown here. Now notice that the teardown process goes in the other direction. We tear down the child first with the implicit call to the child's destructor. And then finally, we tear down the base thereafter. So notice how things are, how this object's being constructed. It's from the ground up. So, okay, this inherits publicly from parent. Let's construct the parent, the base class foundation first. And on top of that, we'll build in the specialization, which will make the child and not some other thing inheriting from parent. Now, when we tear down, we're taking the wrecking ball to the top first, knocking out the child portion. The base portion will still be there till the wrecking ball is taken to the base portion of the class. Now let's, make this a bit more interesting. We would like to initialize a standard library string, str, with a value passed to the base class's constructor. We want the base constructor to set up the base portion of the object, the child constructor to set up the child class's portion. So notice at this point, all I've done is I've introduced a single data member, and it's private to parent. So string is not going to be directly accessible in any function scoped within child. So how do we set that? Well, let's first, create a means to actually initialize that. So we'll create a parameterized constructor that will take a single standard library string as its argument, and it's going to initialize that private data member str. So how we're defining that is simply using an initializer list, taking in an argument, str, using it to initialize, whoops, I didn't mean to delete that. Using it to initialize the data member str. And I'm sorry that this is deviating from the Google style guide in terms of, how these data members and functions are named. Just, ignore kind of the style discrepancies from what you're used to and focus on the process here. So we have this parameterized constructor now for the parent. The question now is, how do we call this constructor during the initialization of a derived class? Well, what we can do is we can create a new parameterized constructor, because if we're creating a child object and we want to give the parent's str data member some sort of information or some sort of value, we have to get that value, right? So the child is going to need to have a parameterized constructor defined for it that is going to take a string as its argument. And then what we're going to see here is once we take that string in the parameterized constructor of the child, we'll just pass it along to the parent's parameterized constructor. So how do we do that? Well, we'll specify that this is to happen in the initializer list. So notice how we've defined parameterized constructor for child, takes in single argument, which we're going to pass on to the parent's parameterized constructor. And we do that by just simply calling the parent's parameterized constructor. In this case, parent is the name of the constructor. And which constructor are we calling? That which takes a single string argument. How do we know that? Well, we're passing a string argument to the constructor. The compiler will go ahead and look and go, okay, does the parent have a parameterized constructor that takes in a single string argument? Okay, it does. We're using that one. And just to make that clear, this would be declared right there, parent std string. And we can see here that this matches that. So this definition will be used, and we can see that str will be used to initialize that parameter, which is then in turn assigned to the private data member of the parent component of that object. So again, we're building up from the foundation first. So we have parent, there's where that single string is going to live. And then on top of that, we build up the child portion, which occurs here, or if there were more items within the initializer list. Okay, so we go ahead and we run through this now. Let's say child P, hello world, we're passing it in, we're essentially passing that up to the base. And notice here I had a single getter for that private data member, and because we're using the public mode of inheritance, getString is going to be able to be invoked by an object of the child type. We inherited that. So if I call p.getString, what the compiler is first going to do is check within the scope of the child class. Hey, is there a definition of getString? There isn't. So where is it going to check next? To see whether or not the parent has provided one. In this case, the parent has provided a definition of getString, so the parent's version will be used. And again, just after compiling and running, we can see here, as we're constructing P, the parent's parameterized constructor will get called, the child's parameterized constructor is called, and then we can print out the contents that are stored in the parent's portion, str data member, and then we begin the destruction process. Now, even though we're not working with dynamic memory in this class, we're going to declare and define the copy assignment operator. And this is going to be because it's going to introduce this idea of name hiding. So think back when we did something like this, and I believe I introduced this in, I don't even remember which lesson, but let's say int I equals 9. Remember that curly braces in C++ introduce a scope. In this case, we can reintroduce a name within, say, a nested scope as we've done here. Between the curly braces after the point of declaration, I is going to be referring to that object initialized with I. Directly once we're out of that nested scope, so here, I refers back to the object initialized with A. If we didn't have that declaration within the nested scope, notice that all references to I here would be referring to that object I, because it's visible, it's nested, and if it's declared in an outer scope, you can see it in the inner scope. Okay, where are we going with this? Well, let's see here. So let's say we define for the parent object a copy assignment operator. And it's going to have single parameter, constant reference to object of same type. And we're just going to print out, hey, we're here, do a couple of things, and cool. Now let's go ahead and go to main and say, okay, let's create an object P, initialize, passing in hello world to initialize the parent's str data member, create another child object P2, and then let's do assignment. So this statement right there is going to invoke the copy assignment operator. And then we're just printing out some contents to see what happened. So given that we overloaded operator equal in the parent class and that the child inherits from the parent with public visibility, child inherited the parent's operator equal. So remember, an explicit or implicit conversion exists from the derived type to the base type, or from, in this case, child to parent. So when we kind of look at all of our functions available to us, we inherited a definition of copy assignment from the parent, and it's going to be the best match despite the fact that we're interacting with child objects. So as we're running through this, we can see, okay, construction of those two objects. So P, I think that's P, P2, and then the assignment of P is equal to P2. The parent's copy assignment operator is invoked because, again, that was the one with the best match. And then we see the destruction process as previously described. So we would like to write an overloaded operator for our child class, given that the child should manage the child components, which are none at this point, but let's just see the implications of this, and parent the parent's components. The definition and declaration that we come up with is as follows. Typical copy assignment operator, as you've seen before, for the child portion. And we're just printing out, hey, we're within this function body to clearly communicate to y'all what's happening here. They're hopefully clearly communicating. So let's see how this has changed what's happened. So after overloading the child's operator equals copy assignment operator, we see that the parent's operator equal is never called. Why? Well, we're dealing with, in this case, the name hiding, right? So we had, this example of int I equals 8, nested scope, int I is equal to 9. Notice here that in this case, within the scope, I is going to refer to the object initialized with 9. If I had not been declared there within this nested scope, we'd look at the outer scope. So we'd go, okay, it's not defined within the scope I'm currently in. Is it defined in the outer scope? Well, an inheritance scheme with, say, the base and derived class is going to create a nested scope. The derived class you can think of being that inner scope, and then the base class is going to be the outer scope. So if a name, so that could be a data member or a behavior, or excuse me, a member function, has not been declared within the derived classes scope, it will then check the base classes scope to see whether or not a definition has been provided. In this case, we first checked the derived class and we found a best match. So which function is going to be fired off? The child's copy assignment operator. So in this case, only the child's copy assignment operator has been called. And we probably wanted the parent's copy assignment operator to also be invoked. The reason why is because how we'd lay this out or how we'd go ahead and define this is we'd want sorry, I keep tapping my Apple Pencil and then it goes to erase. We want the parent's portion to be maintained by the parent's copy assignment operator. And we want the derived classes portion, so in this case, child, to be maintained by the child's copy assignment operator. If we provide a definition of a parent, I don't want to copy and paste that code into the child's copy assignment operator and then having it kind of setting up both the child and the parent portion. And in a lot of cases, that won't even be feasible because the child thing scoped to the child class doesn't have access to the private data members of parent. So how do we go about this? Well, we simply ensure that we call the parent's operator equal. And to do that, so the parent's copy assignment operator, and we pass it the object that was passed to the child's copy assignment operator. Notice here that, again, because we have that implicit conversion of, say, objects of the child type to the base type. And in this case, we're passing by reference. So we're just changing the lens in terms of how we're looking at this object. So in the parent copy assignment operator, we'd be looking at this object through the lens of the base portion. What that means is now, because we're going to be in a function scope to the parent's class, we'd actually have access to the private data members so that we could set up the base portion of that object. And then we could return from the parent's copy assignment operator. And then, here we could focus on initializing the child portion. And again, this is a separation of concerns. We always want the parent to be responsible for the parent's portion, the child to be responsible for its portion of the object. So after adding this explicit call to parent operator equal and the child's copy assignment operator, we're going to have the desired behavior. And notice here, it shows that child's operator equal is called first. Well, yeah, because we have to get into its body to actually invoke the parent's copy assignment operator. So I know that was a bit long, but hang in there. We're almost done. There's one more example I want to run through, which will square away the topics that I was looking to introduce for inheritance. And then in the subsequent lessons, we'll get into polymorphism, which will extend this kind of idea of inheritance a bit further.